Okay, we're going to do a question about the photoelectric effect. So the question says that a clean metal surface is illuminated with light, monochromatic light of wavelength 450 nanometers, and as a consequence, electrons are emitted from the surface of the metal. So this is the basic idea behind the photoelectric effect. If the same intensity of light but of a different wavelength were illuminated upon the surface, how would that change the outcome? So here's our basic question. Lambda equals 450 nanometers. Electrons are ejected. If we change the wavelength to 400 nanometers, will more electrons be emitted? So I'm going deliberately slow to give you a chance to think about it. What do you think? Do you think more electrons will be emitted, fewer electrons, or no electrons? Okay, so let's draw a new picture and add some more detail, right? So imagine now case 2, lambda equals 400 nanometers. Now, one of the rules about the photoelectric effect is that one single photon liberates one single electron. And in fact, this was the way that the existence of photons was first proposed, and this was the first evidence for their existence. It was published in Albert Einstein's famous paper written in 1905. So, single photon ejects single electron. So, if we make the wavelength shorter, no matter what we do to the intensity, one photon is still going to eject one electron. So if we say the intensity is the same, if by that we mean that the same number of photons are present, then the same number of electrons will also be emitted. So hopefully that makes sense. So that would be, I guess, question A. If we change lambda, will more electrons be emitted? And the answer is no. Question B, does the energy of the electrons that are ejected change? Now, what do you mean by energy? We mean the kinetic energy, in fact. Does the kinetic energy of the electrons change? Okay, well, if one photon gives all of its energy to one electron, then the electron would have the same amount of energy that the incoming photon had. So, the energy of a photon is proportional to the frequency of the radiation, and its proportionality constant is Planck's constant. So here we have hf. So h is Planck's constant, which has the value of 6.63 times 10 to the minus 34 joule seconds. And this is the frequency of the light. Now we also remember that c equals f lambda, that the speed of light is equal to the frequency of the light multiplied by the wavelength of the light. So we can replace our f by, let's see, f must be c over lambda, so we could write hc over lambda. So now we've got our E phot in terms of Planck's constant, speed of light, and the wavelength. And the wavelength is the information that we've got. So in the first case, let's see what we have. Let's call it E1, then is 6.63 times 10 to the minus 34, divided by 450 times 10 to the minus 9, and that gives us our energy, which is 4.446 times 10 to the minus 19 joules. Now, we also in physics are often accustomed to writing the energy in terms of electron volts, so let's write it in electron volts also. So electron volts, that will be divided by 10 to the minus 19, which is the charge on the electron, which gives us 2.78 electron volts. So that's E1 in either system of units. So in our second case, what's the energy of the photon? E2, so same thing again, 6.6 times 10 to the minus 34, this time over 400 times 10 to the minus 9. You notice that I forgot the 3 times 10 to the 8 up there, so let's just stick that in, times 3 times 10 to the 8, and then for this case, what are we going to get? We get a different answer. This time I get 3.126 electron volts. So remember, to get to electron volts, we're dividing this whole thing by 1.6 times 10 to the minus 19. So that's E1 and E2. So we can see here that in the second case, when we made the wavelength shorter, the photons had more energy, so you would expect that the electrons would also have more energy. But there's a little bit more to it than that, of course, because in the photoelectric effect, what is the energy that the electrons have as they come out? Well, the kinetic energy of the electrons equals the amount of energy that they got given by the photon minus the amount of work that they had to do to escape from the metal. So in the metal, there are positive charges, aren't there? And the electrons are negatively charged, so the electrons are attracted to the positive charges in the metal, and it takes a certain amount of work to get them out. So that amount of work is called the work function, and it's just the amount of energy that it takes to get the electrons away from the positive charges in the metal. So in our two cases here, in the first case, we can infer that the work function of the metal must be less than 2.78 electron volts, because that's the amount of energy the photons gave the electrons. So if the work function had been 2.78 electron volts or more, no electrons would have been ejected. So what could this metal be? So I went and did some research online, and I found that potassium, for example, has a work function that is very, very low. Potassium has a work function of just 2.3 electron volts. So in this case, case 1 or case 2, we can ask how much energy did the electrons have. So the kinetic energy of the electrons in the first case could have been 2.78 minus 2.3 which is 0.4 electron volts. That could have been the maximum kinetic energy of the electrons in case 1. And in case 2, the maximum kinetic energy could have been 3.126 minus 2.3. Not 0.826 electron volts. So that's how we figure out the energy of a photon. That's how we figure out the energy that is given to the electron. And this is how we figure out the amount of energy that is left over after doing work to escape from the metal.